So, ladies and gentlemen, today's class recording has started. So, at the beginning of this semester, right when we came back from winter break and we took our semester exam, we started getting into the quote-unquote chemistry portion of this class. And one of the first things we talked about was atomic structure. And one of the first things we talked about in atomic structure was Dalton's atomic theory. Okay, does that sound familiar? Yeah. Okay, so Dalton said a couple of different things about atoms, and that matter was made of atoms and a couple other things. But one of the things that he said was that all atoms of a specific substance are the same as each other, but then atoms of different substances are all different from each other. So each substance has a unique atom that goes along with it. Okay? And then, as we start learning more and more about it, right, we get to the realization that atoms are made up of protons, neutrons, and electrons, and each atom is different by the number of protons that it contains. Good? Okay. All right, so then we start looking around, and we find out that there are somewhere in the neighborhood of 120 unique atoms, right? And we list them on the periodic table, and there we are. But if we were to look around this room, we could probably find more than 120 different things, different substances, right? Okay? So, every substance in this room can't have its own unique atom, right? Because there's more than 20 of them, or 120 of them. So, there has to be a way for those 120 unique atoms to come together and make other things that are different from the 120 atoms that we already know about. Does that make sense? Right? And that's what gets us into chemical bonding. Okay? So, what is chemical bond? By definition, a chemical bond is an attractive force that holds atoms together. An attractive force that holds atoms together. Okay? The next thing on your outline, it says, the formation of chemical bonds involves blank. Any guesses what goes there? There's a couple ways you can go with this. Oh, go ahead. It does involve electrons. That isn't exactly what I was going for, but it does involve electrons. And we'll talk a lot about that today. Why do things happen out there in the universe? This goes back to one of those big ideas of physical science. When we talk about why things happen, what's the answer? That's sort of how things happen, not sort of why they happen. There's one word, right? Ready? Why does this happen?
Gravity.
No, gravity is how it happens. Why does it happen? What?
Natural.
Work is done because we're changing what, Eric? Yes, we're changing energy, right? Things happen because of energy, right? That's why things happen. Whether we're talking about this baseball falling in this classroom, or whether we're talking about atoms joining together in a chemical bond. Right? Formation of chemical bonds involves energy. I said that energy is one of those big ideas, right? Those big ideas of physical science that we just keep seeing over and over and over again, just how it applies in this situation. Generally speaking, when we're talking about energy, why do things happen? Things happen in order to do what with the amount of energy that something has? Why does this ball start here and end up there?
Gravity.
No, gravity is how it happens. Why does it happen?
Force acting.
How much energy does it have down there versus up here? It has the same as it's falling when it gets to the bottom, when it hits the ground. Not none, but little, lower. Things happen Things happen because they end up with less energy than we started with. Naturally, things happen in order to get objects, mass, whatever it is, to a lower energy state, right? What's the first orbital that gets filled up with electrons in an atom?
1s.
1s. Why is the 1s orbital the one that gets filled up first?
Closest to the nucleus.
Closest to the nucleus, but from an energy standpoint, how much energy does it have compared to all the other orbitals? It has the lowest energy. That's why it gets filled up first. Things happen to get us to a lower energy state. Meaning, bonds form between atoms if they have less energy together than they did separate. Does that make sense? That's generally speaking why anything happens. Why does this baseball fall? Because it has less energy at the bottom than it did at the top. Okay? So, that being said, those atoms want to get to a lower energy state. But can they just poof, energy go away? No, right? So what do they have to do when they bond to the energy that they had when they were separate? They have to lose that energy, right? So generally speaking, we see bonding as what we call an exothermic process. If you know English, you could probably figure out what that word means, right? If it's referencing something being thermic, that's going to involve what? Heat, right? Or energy, okay? If it's exo, right? What is that telling you? Outside, right? So we're giving off heat or giving off energy, okay? The products have less energy than the substance that you started with. We end up with things that have less energy than what we began with. And what do they do with that energy? They just give it off. We generally see that as something getting hot or something like giving off light, right? A fire is an exothermic reaction. It gives off light and heat as there are chemical reactions occurring in the fire, right? So exothermic involves giving off energy as something is happening. Okay? Good there? And finally, bonding deals with valence electrons. And that's a term that we've introduced before. Where are valence electrons? Outermost shell. And then as far as its relation to the nucleus, what are we talking about? Farthest away from the nucleus. So bonding deals with valence electrons. Electrons in our highest energy level from the outermost shell or the farthest away from the nucleus or whatever we want to say, right? Okay, good so far? All right. Here's an exercise that I've had you do before, but to make a point, I want to start with it again today. Okay? Yeah, here's our good old friend, the orbital filling diagram, right? Okay? So I want you guys, with the help of each other, to write for me 3 electron configurations. 3 electron configurations. I want you to write the electron configuration for lithium, sodium, and potassium. Write me the electron configuration for lithium, sodium, and potassium. No, I want you to write. You guys can do this up at the top, or you can do it in that space. But we're gonna draw something else in that space. Okay. So. Electron configurations for lithium, sodium, and potassium. Go ahead and talk to the person next to you. No. You can do the shorthand electron configuration, right? You don't have to necessarily write all the arrows out. You remember how to do that right away. So, how do those look? Does it look familiar? Right? Let's go that. Oh, good. Yeah, you can do noble gas, that's fine, right? Because, Alec, in this case, right, I had you do this because, like we just wrote in our outline, what are the electrons that we're really concerned with in these three electron configurations? The valence electrons, the end ones, right? So, when we look at lithium, how many valence electrons does it have?
3 or 1.
One valence electron, right? Electrons in the highest energy level. It has 3 total electrons, but 2 of them are in the first energy level, and 1 is in the second energy level. Okay? So that means it has 1 valence electron. Okay? How many valence electrons does sodium have? 1. Right? The highest energy level that we write in sodium is the third energy level. There's only 1 electron in the third energy level. Right? How many valence electrons does potassium have? 1. The highest energy level that we have written is the 4th energy level. Right? There's only 1 electron in the 4th energy level. Okay? Let's do something a little bit trickier, but it's important that we understand this. Okay? What's the electron configuration for fluorine? Electron configuration for fluorine. No, I purposely gave you a not long one. All right, there's our electron configuration for fluorine. Okay? How many valence electrons does fluorine have?
5.
What's the highest energy level that we have written up there? The second energy level. How many electrons are in that second energy level? There are 7. Some of them are in the s orbital. Some of them are in p orbitals, but they're all in the second energy level. Fluorine has 7 valence electrons. Okay? Is that good? Does that make sense? Right? It's not just the highest orbitals we have written, it's the highest energy level. In fluorine, 2 is the highest energy level. That means it has 7 valence electrons. Okay? Good there? We okay with that? All right. But we don't need to know this whole energy or whole electron configuration, because when we're talking about bonding, we said what are the only electrons we're really concerned with? Valence electrons. So let's come up with a shorthand way of representing just our valence electrons, and we do that with something called, oh, bummer, hit the wrong button. Something called a Lewis structure. Okay? So a Lewis structure is a symbolic representation of elements that show the valence electrons. And like it says in your outline, we use the elemental symbol for that atom and dots to represent the valence electrons. Right? So, we look on the periodic table, or we just know, because what is the elemental symbol for lithium? Li, right? And remember when we have a two-letter symbol, the first one's capital, the second one is lowercase, okay? And then we just talked about how many valence electrons does lithium have? 1. So we would draw its Lewis structure like this. Okay? Don't worry about the box so much. If you have Li with a dot next to it, okay? And technically, it doesn't matter where that dot goes. We'll see that there is sort of a pattern, and I'll show you why that pattern exists here as we go along. Okay? All right, we did fluorine as well, right? So, even though we're skipping oxygen, okay? we just learned that fluorine has how many valence electrons? 7, right? So we're going to start off, we're going to write the symbol for fluorine, which is what? F, okay? And then we're going to surround it with how many dots? 7. Now, like I said, there is technically no right or wrong way to do this, but there is a pattern that we use, and there's a reason why we use that pattern, and I'll show you in a second, okay? So, with fluorine, here's how we usually write this, okay? So, we'll start off with the elemental symbol, and then think of it as having like 4 sides, okay? So, we'll go, and you don't have to write them in this order, but just so we end up this way, okay? So here's one of fluorine's valence electrons, and then for the second one, I'll move it up here. For the third one, I'll move it over to this side. For the fourth one, I'll go here, okay? And then we'll go make our way back around the horn, right? So fluorine's bluish structure will look something like that, okay? Which side has the single dot and which sides have the double dots really doesn't matter, all right? So, go ahead. In a way, yes, okay? In a way that we're kind of representing that. We know, Eric, we know that each orbital can only hold how many electrons? 2, right? So we can kind of think of each side of that sort of being like an orbital. It can only hold 2. If we want to think about it that way, that's fine, okay? All right, so that's what our Lewis structure for fluorine looks like. What's the one right next to fluorine?
Chlorine.
Chlorine. You look on the periodic table. Where is chlorine?
7A.
It's in 7A or group 17, right? More importantly, it's in the same family as fluorine, right? So what does that mean?
7.
Has the same number of valence electrons. That's why they behave similarly, right? So the Lewis structure for chlorine is going to look like this. And here, when I draw this one, right, I'm not just going to go around the horn. I kind of know what it's supposed to look like, and we'll go from there. Okay? All right, good there with those 3 so far? Okay? So, let's talk about the one we skipped. Let's talk about oxygen. Where is oxygen in relation to fluorine? 1 to the left. So from a total electron standpoint, how many electrons does it have compared to fluorine? 1 less, right? If we go back to our electron configuration for fluorine, right, that for oxygen, that 1 extra electron or that 1 less electron is going to come out of that orbital, right? Does that make sense? Yes, no, right? Yeah. So, if we take this from 2s2, 2p5 to 2s2, 2p4, how many valence electrons does oxygen have? It only has 6 valence electrons, right? So, when we're drawing a Lewis structure, we'll draw capital O to represent oxygen symbol. 1, 2, 3, 4, and then, and this is where it kind of, oh, sorry, I should have done it this way. Okay. Let me erase those here. Okay. The going around the outside thing helps with this, because when we do that, 1, 2, 3, 4, 5, 6, we see that there's 2 electrons that don't have a pair, right? If you were to draw 2, 2, and 2 and leave one side completely empty, technically that would be okay, all right? There's a reason why we draw it this way. When we start getting into the bonds that oxygen forms, it'll make a little bit more sense. So that's kind of how we do it this way. Okay. All right? Then the last Lewis structure that you guys have on your outline is neon, right? Where is neon in relation to fluorine? 1 to the right. So it has how many electrons?
8.
Well, it has how many total electrons? 10. So it has 1 more than fluorine, but that 1 more is going to go right here, right? It's these 2p orbitals that fluorine has aren't full. It can hold 1 more electron, right? So that takes now our valence electrons from 7 with fluorine to how many for neon? 8, right? So when we draw neon's Lewis structure, it's going to look like this, right? Right? 1, 2, 3, 4, 5, 6, 7, and 8. Yeah? Good there? We okay with Lewis structures?
It's pretty easy.
It is pretty easy. Okay? Now, why do we draw these Lewis structures? Well, we kind of talked about that. There are 4 sides to this symbol, right? And we kind of go around the horn and fill them in, right? 2 on each side because we know each orbital can hold 2 electrons. When we get to neon, what are we seeing about all 4 sides of its Lewis structure? Filled, right? With 8, so now it has 8 valence electrons. And we'll find out that's important when we start looking at the behavior of these atoms, okay? So what we find out is the number of valence electrons determines the chemical properties of the element. Okay? When we talk about chemical properties, we're basically looking at what atoms will an element bond with and what atoms will it not bond with. So when we talk about chemical properties, we're looking at forming bonds. What atoms will it join together with? What atoms will it not join together with? That's a shorthand way of chemical properties. But whether they join together or not join together is always driven by one rule. And that one rule is we are trying to get to 8 valence electrons. 8 is the magic number when it comes to valence electrons. Let's make some connections from the beginning of class. Why do atoms want to get to 8 valence electrons?
So, it's stable.
Yes.
When it's stable, it has the least amount of energy.
Good job, everybody. Right? 8 valence electrons is a stable amount of valence electrons. And that corresponds to the lowest or a lower amount of energy than not having 8 valence electrons. Okay? So, atoms are trying to get to 8 valence electrons, but there are 2 ways that that can happen. Some atoms will gain electrons to get to 8. Some atoms will lose electrons to get to 8. Ugh. I have a spelling error on the screen, and it does it every I do it every year. So it's a loosing, right? That means I'm making it looser. That's not what it means. Right? It means losing. Is it? So when you're writing it on your outline, don't put the second.
I
in
did
there.
actually.
Okay. So, okay.
It's probably something that
You guys.
Yeah, I did.
Nice, Julie.
Are you guys like Ron Burgundy? Will you write anything that I put up here on the screen on your outline? So. All right, so let's go back to our electron configurations. Okay, and let's talk about fluorine. Okay, we just talked about fluorine, but let's talk about it again. Okay, fluorine currently has how many valence electrons? 7. So to get to 8, it has to do what? Gain 1. Okay? But let's take a look at sodium. Okay? We said sodium has how many valence electrons? 1. Okay? So in order to fill up the 3rd energy level, it would have to do what? In order to fill up the 3rd energy level, it would have to gain 7 electrons. Okay? Gaining 1 electron is okay. Gaining 2, alright too. But when you have to gain 7 electrons, right, that becomes very difficult. Each electron that an atom gains does what to the electrons that are already there? It repels them, right? If you have to gain 7 more electrons, those 7 new electrons would repel each other and the electrons that were already there. That's not low energy, that's high energy. Alright? But if we look at sodium, its highest energy level right now is the 3rd energy level, and it has 1 electron in that 3rd energy level. But if it got rid of that electron in the 3rd energy level, right? Now what's the highest energy level? The 2nd energy level. How many electrons are in that 2nd energy level? 8. Is that stable? That's stable, right? So some atoms can gain electrons to get up to 8, but some will lose electrons and get rid of a higher energy level altogether and be left with the previous energy level. They're good. Halogens don't have 8. They have 7, right? Okay. Now, which family does have 8 though? Noble gases. What's one of the properties of the noble gases? They don't do anything. Why? How many valence electrons do they have? They have 8. Do they need to gain or lose any electrons to get to 8? Nope. I'm good. I'm good here. Nothing to see. Move along. Right? So, when we talk about a pattern for what happens, right? When we look at valence electrons, how many valence electrons do the alkali metals have in group 1? 1. How many valence electrons will the alkali earth metals have in group 2? 2. Now, for our purposes, for this discussion and for our section here, we're going to forget about the transition metals. Okay? We're not going to worry about groups 3 through 12. And we're going to pick it up at group 13, boron's family and aluminum's family, right? So if we look, going from beryllium number 4 to boron number 5, that's how many electrons? How many extra electrons? Going from 4 to 5 is how many extra electrons? 1, right? Okay. So that means now group 13 will have how many valence electrons? 3. Group 14 will have 4, group 15 will have 5, group 16 will have 6, group 17 will have 7, group 18 has 8, right? So moving across the periodic table, if you skip the transition elements, which we'll do for this unit, 1, 2, 3, 4, 5, 6, 7, 8, right? But then we go back down to number 1, right? So when we go from fluorine, fluorine has 7 valence electrons, neon has 8 valence electrons, but then sodium has 1 valence electron, because now we jump it up to the next level, right? So that pattern goes like this. We want to end up at 8, whether that means going from 7 to 8 and gaining 1, or that means going from 1 to 8 and losing 1. Right? So, how does that happen? Atoms gain or lose electrons to have a full outer shell, or a full valence shell. We're either going to gain or lose, depending on how many valence electrons we have to start with. Okay. What kind of atoms gain electrons? Generally speaking, what kind of atoms gain electrons? Sammy, go ahead. Halogens, yes. What else? What other family is going to gain electrons? Oxygen family, right? Okay. And then probably also too, nitrogen family as well, right? Because getting from 5 to 8 is easier than going from 5 to 0. Okay? What side of the periodic table are all those families on?
The right side.
Right-hand side. What kind of elements are over on the right-hand side?
Non-metal.
Non-metals, right? What kind of elements are going to lose electrons? Metals, right? So generally speaking, Metals lose valence electrons. Non-metals gain valence electrons. All right? Oh, look at that. Good lead-in, right? So metals are going to lose valence electrons, so their electron configuration looks like the previous noble gas. When I asked you to write the electron configuration for potassium, if you wrote argon in brackets and then wrote 4s1, which you asked me about, right? If you lose that one electron, your electron configuration now looks like what? Looks like argon, right? Because you used the first 18, right? Non-metals will gain electrons to become like the next noble gas. Okay? Now, not all atoms get to 8. Okay? If we look at lithium, right? We said that lithium has how many valence electrons? 1. Has 1. Okay? Lithium is where on the periodic table? Group 1, which makes it what kind of an element? Metal or non-metal? Metal. So it's going to do what with its valence electrons? Lose them. If it loses this valence electron, right? How many valence electrons does it have left? 2. It has 2, which isn't 8. But the 2 electrons we're talking about are in which orbital? 1s. Are there any 1p orbitals? Nope. Right? Is the first energy level full now? Yes. So lithium is stable with only 2 valence electrons because it has a full level. It's just a small level. All right? So that only really applies to a couple elements, right? Once we get past boron or once we get past carbon, we're going to be at 8. But for those smaller elements like lithium, beryllium, helium, even though they only have 2 valence electrons or end up with 2 valence electrons, they'll still be stable. Jack, go ahead.
So hydrogen has to be great.
Hydrogen's weird. That's why we don't kind of throw it into the same column as the lithiums, all right? Because yes, it has 1 valence electron, but if it loses that 1 valence electron, now it has no valence electrons, right? So it's like, yeah, that's a kind of a different situation. So let's not dive too deep into hydrogen at this point in time. Frank, go ahead.
So carbon currently, since it has 4 valence electrons, it's gonna lose because it's non-metal.
Now, what we'll find out is that carbon generally doesn't gain or lose. It does something different. And that's when we get into covalent bonding. Okay?
Trades.
All right, so let's finish up this slide right here, then we'll call it a day, right? We've already kind of talked about it. Noble gases are unreactive. They don't form compounds with other elements. Why don't they form compounds with other elements? They already have 8 valence electrons. They have a stable configuration, and they already exist in a low energy state. Atoms trade electrons to get to a low energy state. But if you're already in a low energy state, you don't have to trade electrons with other atoms. And because they already have their highest energy level full, they don't form bonds with other atoms. So question, does this always mean that there are 8 valence electrons? Do all noble gases have 8 valence electrons?
Yes.
No.
Oh, that's.
The first noble gas in your periodic table is what?
Oh.
Helium. Okay? Helium only has 2, but that's stable for those small atoms, right? All right, tomorrow we'll talk about how the bonds actually form. You'll get to see some sweet animation. When I say sweet, that's completely sarcastic. It's pretty lame, but it works. So we'll get into that tomorrow.